largest centre of physics in Europe. And I believe we have 32 Nobel Prizes. In addition to all of those things, I am also a Christian. I became a Christian at the age of 18, by surprise in many ways. I wasn't planning on becoming religious. I wasn't looking for a religion, but I was surprised by what I found when I, for the first time in my life, read the Bible and learnt about the person which I went to university to study physics. So for me, I've been living this question of science and religion really my entire adult life, because they both started at pretty much the same time. So I guess we could ask of myself, what is inside a believing physicist's brain? I'm sure you're familiar with these brain cross-sections. And some people would assume that a physicist who also believes in God has a brain to learn to keep these two things together, but not too close. I think one of the things I've learned in the 30 years that I've been a Christian is that this is a much better model. That physics and faith are certainly different, but there is a very healthy region of overlap. And actually that overlap, we might be tempted to think, is a place of conflict. In fact, I've found that region of overlap to be a very rich intellectual place, a place where we need to think very carefully, but where there are some really interesting and enriching things can come out. Areas in physics that also impact that faith area. I doubt I'll have many answers for you. I'm going to pose more questions than I answer, but at least I can alert you to some of the new things that are coming out in physics, that are being discovered as we speak, and where I think there is more work to be done at that interface, and maybe some of you can do that work in coming years. So here are the 6 mass, and that over time that explosion began to coalesce, and the fundamental particles began to find each other and to begin to create things like protons, and from there elements like hydrogen and helium, and eventually they coalesced and began to form planets and stars, which coalesced to form galaxies. So essentially the history of the universe has really been one of bringing back together some of the bits that were thrown out from that Big Bang explosion. Interestingly, Dennis mentioned this, but let me give you a little bit more detail. One of the scientists who was most responsible for piecing all of this together is a man called George Lemaitre. And you may well have heard of the Hubble telescope. And that was named after a famous scientist, Hubble, who allegedly first discovered the universe was expanding. But in fact, a lot of his work drew on the work of George Lemaitre. And you'll notice from his neck, his clerical collar there. And George Lemaitre was a Catholic priest. And so if we begin with a conflict model of believing that physics and faith are in opposition, then the very first thing we need to notice is that that most foundational of all physics theories, the Big Bang, was actually brought about by a Catholic priest. And so immediately that should tell us our model of conflict cannot be right. There's a really old argument for the existence of God, possibly going right back to Plato, called the cosmological argument, the cosmological argument for the existence of God. It's one of these really fundamental philosophical arguments. I'm sure those of you who are theologians may have touched on this. And it has 3 steps, and it says that everything that has a beginning has a cause. And the second step is the universe has a beginning, and therefore the corollary of these is therefore the universe has a cause. And from there you get to a belief in God, at least a very weak form of theism. What I find really interesting about this argument is that at the time that it was formulated, nobody really knew if point 2 was true. As late as the middle of the 20th century, we didn't really know if the universe had a beginning, or if it had always been, the so-called steady state argument. One of the contributions that modern physics has made to this very old argument is absolute empirical evidence that the universe did have a beginning. And once you feed that into that argument, it's stronger. So this is one of the ways in which, when I talked about that rich interface between faith and physics, this is one of the ways in which modern physics has helped faith. It's really nailed one of those foundational philosophical arguments about the existence of God. I should just say in passing here as a footnote, this cosmological argument tells us nothing about the nature or the character of God. It's very much a first principles argument that gets you to the most general form of theism. We then need some much more detailed specific. It is remarkable. We sometimes think of Big Bang as being this very well-defined, complete description of the origins of the universe, to the point that some people then push it further and say, therefore, there is no need for God. God of the gaps. I wouldn't want to say that just because there's something we don't know, that means that's where God lives. But nevertheless, I think we should be aware of the weaknesses in theories. And we really don't know most of the stuff that makes up the universe. We call it dark matter. All we know is that all of our models without it would say that the velocity of the universe should fall off at that sort of velocity. It doesn't fall off. We've got to have something there that makes our current models wrong. But as to what the nature of dark matter and dark energy are, we have very little idea. And this is one of the areas that astronomers and theoreticians are working on very intensely. And it may be that in coming years, maybe in the next 10 years, we have a better idea of this stuff. But as things stand at the moment, there are huge uncertainties in our understanding of the origins of the universe, and indeed what makes it up. This is something that we're particularly proud of in the Cavendish at the moment. About 4 weeks ago, there was the announcement from Stockholm about this year's Nobel Prize for Physics, and it was one of my colleagues, Professor Didier Queloz, who is an astronomer in the Cavendish, was awarded a share in this year's Nobel Prize for Physics for the discovery of exoplanets, that is to say, planets which orbit stars other than the Sun. So the Sun is the star at the centre of our solar system, and in recent years astronomers have been very interested to know, are there other stars out there in the galaxy which also have planets going around them? And Professor Queloz was the first to discover one such planet quite a few years ago now. I think it was even his PhD work. But it was finally recognised that this was worthy of the Nobel Prize. And now, I can't remember, is it 4,000 or 8,000? There are several thousand exoplanets have now been discovered. And so we know that the solar system as we know it, a star in the middle and planets going round, we know that that is not unique within the universe or indeed within our galaxy. And this is areas of physics, discovering all of these new exoplanets, and new ones are being discovered every day. Of course, this will raise some theological questions, which I know is your area of interest. It raises the question, how special is the Earth? Is there only one planet like the Earth? Are there only a dozen planets like the Earth? Or are there billions of planets like the Earth? We don't know at the moment, but this is something that we will know fairly soon, I think. It adds more information to the ongoing search for extraterrestrial life. Once you have a planet around a sun, around a star, you have the possibility of life. And we now have the technology to look at the chemical elements in the atmosphere of these exoplanets, these planets going around other stars. And this will give us more information in our search for extraterrestrial life, which is clearly something that theologians then have to blend into an understanding of what it means and what it means for a creator God to have made the universe. I'm reminded of Psalm 19, the heavens declare the glory of God. And I think sometimes, especially outside of physics, there is a temptation to be worried about these new discoveries in physics, as if they are by nature threats to people of faith. Let me say from the inside of the subject, relax. I think we can be very optimistic about these discoveries, because if we start with our fundamental belief that the heavens declare the glory of God, then the more clearly we see the heavens, then the more clearly we see the glory of God, which is something that people of faith are very enthusiastic about. So personally, I think it's great that we're discovering these exoplanets and we're talking about dark energy, because these are all things that in more detail what it is that he has done, so that I can praise him more for it. Okay, so that's all I'm going to say about origins of the universe, just really to signpost that these are some of the things that we're talking about in the physics world. Now here's something I know a little bit more about, because I'm not an astronomer, so I don't really know the detail of the astronomy, but I am a condensed matter physicist, which means I know an awful lot more about this next part. And that's this very new and emerging area of quantum technology. So one of the ways we sometimes describe it is quantum technology 1.0 and quantum technology 2.0. So there is an argument that says we already have quantum technology 1.0. We've had that really since about the 1950s. So for example, if you take a microchip, just crack open your mobile phone or your laptop, and when you break it down into its lowest level component, you'll find a transistor, and the transistor is controlling the flow of electrons through the material silicon. Controls that flow is relying on quantum mechanical properties that leads to what we call band structure. So already in your pocket you have billions of little quantum devices. So in a sense, quantum technology is nothing new. This laser that I'm using to point at the screen, this works by energy transitions in electron energy between quantum states. So again, this is quantum technology, nothing new. And I could add to that list, if you use a sat-nav, if you use the GPS on your phone to work out where you are, you're relying on precision timekeeping by atomic clocks, which is an entirely quantum phenomenon. If you go to a hospital for an MRI scan, you're relying on hyperspectral splitting, a quantum phenomenon of atomic nuclei, to image your body. And if you have a Facebook account or a Twitter account, or you stream anything from YouTube, if you use any sort of cloud service, then your data is stored magnetically in the form of a hard disk drive, and the quantum mechanical effect of tunneling is used to read that data back. So we're already have quantum technology integrated into every detail of our lives. The point is, though, in all of this quantum technology 1.0, the quantum physics makes it possible, but it's a classical thing, a non-quantum thing, that we actually end up using. So it's the quantum that makes the light possible in a laser, but the light itself is classical. We never actually use the quantum property at the end of the day. We just use the quantum property as a means to an end. The exciting thing about this moment in time is that there is a new type of quantum technology just emerging, called quantum technology 2.0, where it's actually the quantum phenomenon itself that we are using. So here is a very early example. I mean, this has got so much further to run, but this is from a company called D-Wave, who have something that approximates a quantum computer. Now, this is a completely new class of computer. It's really got very little to do with computers as you know them. In particular, this type of computer only works at very, very low temperatures. That's why it's got all of this metal surround. This thing's going to be plunged into liquid helium and cooled down to very close to absolute zero. But in comparison to today's computer, what it can do is just remarkable. So they can perform what are called quantum computations, which can be billions of times more powerful than the computations we do today. They can be used to simulate quantum mechanics, and that gives us a new way to simulate nature in a way that's never been possible. And there's all sorts of other applications. And I think there are theological implications. Now, if you'll forgive me, this is one tiny, tiny bit of advanced physics. Please go to sleep for 10 seconds if you're struggling. But I would argue that quantum technology 2.0 is taking us as humans into a whole new area of existence, into the quantum world. So one of the little bits of physics that we sometimes use to describe quantum phenomena is called the Bloch sphere, or sometimes called the Poincaré sphere. And think of it as a sphere. Think of it as like a tennis ball, and a quantum state is represented by being at any point on that surface. So any place on the globe, if you like. And the point is, the classical places, so the non-quantum places, are the north and south poles. In simple terms, everything before quantum technology 2.0, so basically the modern world as we know it, has only used on that surface, the North Pole and the South Pole. It's as if, as a species of explorers, humans only lived at the North Pole and the South Pole, and we haven't yet discovered India and America and Europe and all of these other places. We were just living on a little iceberg at the top and the bottom of our planet. And that's what's happening in quantum technology 2.0. We are leaving the poles and we are moving across the whole of the surface of the Bloch sphere. I say this to try to emphasize just how different quantum technology is and how much of a new world it will allow us to explore. And so there are a lot of theological questions that are going to come out. We will have vastly more powerful computers, billions of times more powerful, and those can be used to drive artificial intelligence and machine learning, which will make today's AI look very, very primitive indeed. An area that's emerging, which blows my mind actually, is what's called quantum biology. The initial observation that maybe some really fundamental phenomena in biology, like photosynthesis, actually rely on quantum mechanics to get their efficiency. Could it be that humans, our cells, are actually little quantum machines? At the moment we have very little way of exploring this, we don't know. But it could be in coming years we completely rewrite our understanding of those most basic biological processes like photosynthesis and human cell operation. I'm reminded of Psalm 139, which talks about God knowing everything and God being everywhere. Before a word is on my tongue, you, Lord, know it completely. You hem me in before and behind. Where can I go from your spirit? Where can I flee from your the heavens, you are there. If I make my bed in the depths, you are there. Quantum technology is suddenly expanding the number of places that we can go to. And while I don't see that as a threat to our theology, I think we will have to reevaluate how we understand God being everywhere if he's also to be in all of the quantum spaces as well. Perhaps we can come up with some nice descriptions that describe just how omnipresent God is, that takes into account not just the top and the bottom of the Bloch sphere, but everywhere. And this is a work for theologians who are also scientifically literate. But again, as I say, no threat. God is still sovereign. God is still above it all. I think we just get to see a bit more clearly how great and how amazing the things that he is above actually are. Okay, so origins of the universe, quantum technology. Third area, randomness and uncertainty. And this is an area where our thinking is evolving very, very quickly at the moment. So, and again, this is related to quantum mechanics. Again, forgive me for that, but there's no other way to do physics really. And in quantum mechanics, we talk about states, state A or state B. These are very abstract things. The famous Schrödinger's cat, you may have heard of Schrödinger's cat, in a sense was meant to be a parody of this, because a cat can be in two possible states. It can be alive or it can be dead. And the parody said, well, it has to be one or the other. Because quantum mechanics argues you can either be in purely state A, or you can be purely state B, or, surprisingly, you can be in a mixture of state A and state B. And if we think back to our Bloch sphere, the poles are the pure states, and then everywhere else over the surface of that sphere are the mixed states. And just to give you an idea of how unusual quantum mechanics is, particularly with regard to randomness, let me just give you a little example from something that will be very intuitive to you, and that's to do with mixing of colours, of either paint or of light. I've chosen the wording to work for light, but it would work for paint as well. So if I have a mixture, you can't really read that, if I have a mixture of red, blue and green light, we all know that the human eye doesn't see red, it doesn't see green, it doesn't see blue, it sees white. Yeah? That's a classical way of looking at these things. If you saw things with quantum eyes, what you would actually see is a third of the time you look at it, you would see red, a third of the time you see it, you would see green, and a third of the time you look at it, you would see blue. And as to which of those you see would be a random choice that the system makes for you. And so, into the process of observation, we suddenly have built this random element. And this perplexed Einstein very much. Einstein famously said, "I cannot believe God plays dice with the universe," which was his way of saying, I find it almost unbelievable that a random choice should be made for me as to which of these three colours I see, rather than our more intuitive view that you see a mixture of all of them, which we call white. So we suddenly find, modern physics suddenly tells us that randomness is at the heart of virtually everything. And that can be perplexing to everyday people and also to theologians. And yet even more perplexing is that in our minds, when we think of randomness, we think of something that's unpredictable and uncontrollable. I recently went to a conference in Las Vegas, probably the capital of random phenomena, all of those roulette tables and slot machines. And that's certainly out of control. Everything about Las Vegas is out of control. The surprise of quantum mechanics is the randomness leads to perfection. So if you look at a street lamp, which works by exciting sodium, it doesn't matter if it's on the streets of Bristol or on the streets of Bangalore. The colour or the wavelength is always the same, 589.3 nanometers. And the reason it's exactly the same is actually because of the randomness of the quantum mechanical processes that drive it. And so out of the randomness of quantum mechanics comes the precision of precisely defined energy levels. And this is something big for the theologians to grapple with. Here's just a list of some of the questions that theologians need to ask about it. What about God's knowledge? Does God know in advance the outcome of one of these random quantum observations? How do we understand those theological characteristics of God, his omnipotence and his omniscience, in a quantum world that's dominated by random processes? How do we understand perfection? How do we understand design? We always think of those things in very Victorian terms, that everything is precise and mechanistic, and yet we discover at its heart our world has this big roll of dice going on. How do we understand emergence, where the perfection comes out of the random? Now personally, I don't think these are particularly threatening things. I think actually Scripture preempts some of them. So for example, Proverbs 16 talks about the lot is cast into the lap, but its every decision is from the Lord. Here's a really nice example of how things that are random to us still fall into God's omniscience. But nevertheless, these are important areas that theologians. Okay, fourthly, mind-body problem. This is one that I get very excited about, so I'm going to get very animated in the next few minutes. So I'm sure many of you know this term, mind-body problem, but it's this very old philosophical question of what is the difference between the mind and the body. On the one hand, the brain is just another organ. We can understand through medical science how it works, and yet the output of that organ, consciousness, humanity, is something we can't understand. And where is the interface? Where does it stop being the physical organ of the body and become something much more difficult to get a hold of, the mind? So this is called the mind-body problem. And one of the really interesting bits of modern physics, and this is so hot, it's almost on fire, is what we call neuromorphic computing. It's impossible to go to a conference in physics these days and not find somebody who's suddenly discovered neuromorphic computing. This is how we do computing at the moment. So any student of electronic engineering or of physics will have spent hours and hours in lectures working through these so-called Boolean logic gates. We build, so everything from a mobile phone through to this computer, this data projector, they're all built by cascading these so-called Boolean logic gates together. There are 4 of them, 4 fundamental gates. And from a combination of those 4 basic gates, we can make anything electronic. What's interesting is the human brain doesn't use those. The human brain isn't constructed using Boolean logic gates. The human brain looks very different. It's made from neurons and synapses connected in this very complex network. And for a long time, people have recognized that the fundamental architecture of the way we build computers is so the way nature builds computers, brains. We've even given them names. So the way we build computers, we call that a von Neumann architecture. The way nature builds brains, we call that a neuromorphic. Physicists using words to describe the same thing. Remember, neuromorphic, morph just means the shape of, the neuro just means the brain. So it's an architecture that's in the shape of a brain. And so for a long time, people have been saying, well, why can't we build computers using a neuromorphic architecture? Why can't I build a computer that uses the same design as a human brain? Surely that would be an interesting thing to do. And here's why not. There is a missing component in our physics toolkit. So all of electronics works on 4 fundamental things: voltage, charge, current, and flux. And the way we think of all the electronic components that make up electronics are really devices that convert between these 4 basic elements. So for example, a resistor is a device that converts from voltage to current. That's what Ohm's law is. And that's what it looks like. You can buy these for ₹1 each. A capacitor is something that converts between voltage and charge. And again, that's what they look like. You buy those for ₹1 each. An inductor converts between current and flux. We've known this for 100 years. We've also known that we don't know what converts between charge and flux. And Dennis was talking about elegance and symmetry and beauty this morning. And just purely by the simplistic completeness of that diagram, surely there must be a component out there that converts from charge to flux. But we don't know what it is. We don't have them. I can't send you to a store to buy one for ₹1. It's relevant to neuromorphic because if you look at how a human brain works and say, well, which component on this spectrum is it most like? It is most like that missing component. Here's the exciting thing. We've just discovered it. It's called a memristor. This is what it looks like in practice. It's a nanotechnology component. I can't just go and buy them like I can buy all these other components. But they absolutely exist, and they've been made now fairly repeatedly for the last 10 years. And they absolutely convert charge into flux. And now that we can build a brain. And so we could imagine a device that looks like a microchip with arrays and arrays of components, just like in a memory chip or a microprocessor, but where each of those components isn't a transistor, it's not a resistor, it's not an inductor, it's not a capacitor, it's a memristor. And if we can do that, in principle, we can begin to build electronic circuits that mimic the architecture of a human brain and maybe begin to function just like one. Combine that with all of the things we're learning very quickly because of the advances in brain imaging. So Dennis mentioned functional MRI and things like that. These imaging techniques coming from quantum physics are advancing very, very quickly. So we can see through functional MRI different parts of the brain light up as people think about different things, as they pray even. Data coming into that. The outcome is expect a lot of progress in the next few years on the mind-body problem. I'm not saying we're going to solve it, but there's going to be a lot of new data coming very, very quickly. And so that means the theologians have to get to work and start to answer these. Does a neuromorphic computer have consciousness? If we can pretty much build something that's identical in structure to a human brain, maybe it can. Does it have rights? Does it have a legal personality? If I turn it off, if I just murdered it, Could I be prosecuted in court for that? Lots of ethical decisions to be made as well. And this gets us back to that really fundamental question: what is the essence of being human? Humans are Homo sapiens. The sapiens bit reminds us we've got big brains. We've put so much store in the past in our unique defining feature as being this great big computer on our shoulders. But what if we can build one? Is that the right way to define humans? Or should we actually be thinking, as, say, theologian John Stott did, that our primary definition is homo divinus, people who are capable of relationship with a creator God? That's what makes us special, not the ones that we've got. And there's a real teaser for you. How do we soul in the presence of a Turing test passing machine? So this idea that I could build an artificial intelligence machine that is indistinguishable through a question and answer interrogation from a human being. And I'm pretty sure that the combination of neuromorphic computing and quantum technology too will give us one of those very, very soon. There may be an argument that says we already have. Assume that in coming years we have mechanical devices, if you like. We have synthetic engineering devices that can pass the Turing test. Where is the soul in a human if I can't tell if I'm talking to a human or a machine? These are big questions for theologians. Okay, let's keep moving. So, Dennis has actually mentioned this one completely, so I'll go very quickly on this. But this is something where people of faith are streets ahead of atheists. And it's really that question: why do maths? Quite often people have to be in science for some time. This is a remarkable thing. But many of the greats of the past have realized so Einstein was very aware of this, and Eugene Wigner, who those of you who've done basic physics will know the Wigner Zeitzel and all these sorts of things. This is the man who was behind them. So he talked about the unreasonable effectiveness of mathematics in the natural sciences. There's no reason why mathematics should be able or should be useful as a modelling tool in the world. And likewise, Einstein wrote a paper in 1936 where he talked about the eternal mystery of the world is its comprehensibility. The fact that it is comprehensible is a miracle. Add to this and say, absolutely, it is a truly shocking thing that maths and physics work. Of course, those of us coming from a faith perspective say it's the most natural thing in the world, because as Augustine of Hippo said, nature is what God does. These things work because they reflect the Creator who is operating through them. Finally, fine-tuning or anthropic. So this is something that everybody should be aware of. So if you would like to just come back to life for a couple of minutes, because this is a basic science observation that every person of faith should be aware of. And it's this observation from physics, nothing to do with faith, purely from physics, that the fundamental constants of the universe, even if they were slightly different, wouldn't allow life to be possible. So when I say the fundamental constants of physics, what I mean is there are some things that we can calculate, and there are some things that we can't. There are some things we're just given. So things like the speed of light. There isn't an equation that gives you the speed of light. It's just one of those numbers that is as it is, and we don't have any particular reason to believe it's derived from anything. It's just a fundamental fact of the universe. And many years ago, physicists realized that there were roughly 6 of those fundamental constants, that even if they were ever so slightly different, the universe would look so completely different that there would be no hope of life. So for example, these are really fundamental things. If one of these was ever so slightly different, then there would only be hydrogen in the universe, only one element. We wouldn't have helium or carbon or nitrogen or phosphorus. And you just can't imagine life if you've only got one element to play with. There's just not enough complexity there. If another one of these constants was slightly different, then the sun would have burnt up all of its nuclear fuel really quickly, too fast for life to evolve. And so again, the universe would be empty and sterile. And so why is it that these constants that we don't believe have any particular reason for having the values they do, just so happen to have all of the perfect values to make life possible? And so this is why it's called the fine-tuning argument, because it looks as if somebody has fine-tuned all of the fundamental constants of nature that life can exist. Now, of course, this is consistent with the idea of a creator God. If, like me, you're a person of faith, then it's perfectly obvious that these constants should have been tuned, because God wants there to be life, and so he's arranged that there should be. If you're Professor Dawkins, you have more of a problem, because he doesn't have any guiding force to allow those constants to have the values that they do. And of course, atheist physicists have an answer. They say, well, it's multiverse. Multiverse is a particular interpretation of quantum mechanics, and I have to say, from the inside of physics, it is science fiction. To rely on multiverse as a rational scientific explanation of something is completely unscientific. It is so speculative and so unproven and possibly so unlikely to ever be proved that it doesn't count as a scientific explanation. I would though like to take 2 minutes, if I may, to give you the other side of the argument on fine-tuning, because you may hear these things from other people, and so it's good to talk about them. So here's the but. The big but is, do we know the volume of the parameter space well enough to say that the current universe is improbable? Here's a little drawing to show you. So here's just constants. There are 6 in total, but I can't draw 6, so I'm going to show you 2. These are the 2 values that you need for those 2 constants for life to be possible, and that is indeed the values they have in the universe as we know it. Now we could say, well, how far off could those constants be and still allow life? And so that will give us an area of possible life there, the green box. The question we've then got to say, could they have in principle? And we'll call that the red box. And then simple geometry tells you the probability that the universe can sustain life is just the area of the green divided by the area of the red. This is a simple probability argument. The trouble is, we don't know the area of red. Because we have no idea where those constants come from, we have no right to say what range of values they could have. And so some philosophers of science say the fine-tuning argument doesn't work because we can't talk, we don't know those areas. In simple terms, the question is, do we have the right to be surprised at our current universe if we couldn't exist in any other universe, or if we don't know of any other universe? And another risk, is this actually just us making the God of the gaps mistake, because at this point in our physics understanding, we don't know where those constants come from, and that maybe in 100 years' time we will, and we'll find they're not fundamental, and they can be derived from other things, we just don't know. And so, urge a word of caution that we don't commit the God of the gaps error because of our current limitations of physics knowledge. So here's my personal view on the God of the gaps. I notice how readily when they're trying to deny the theistic implications of fine-tuning. So I would say there is much more empirical evidence for the resurrection of Jesus, the existence of multiverses, and yet alleged physicists who are also atheists will immediately quote multiverse in order to get out of the fine-tuning argument. So there is a huge inconsistency. Dennis talked about falsifiability and Karl Popper and all of these people. The multiverse has to be non-falsifiable by definition. Notice how quickly atheist physicists accuse theists of believing in things that are non-falsifiable, while they themselves draw on non-falsifiable things like multiverse to get out of fine-tuning. My advice is, don't believe in God because of fine-tuning. Believe in him because of Jesus Christ. But once you do believe in him because of Jesus Christ, then fine-tuning is no longer a surprise, but rather it is consistent and to be expected. And I think that's the way round they should go. Don't build anything tuning, but once you've already got faith, enjoy the extra reassurance that it gives. Okay, time is gone. Let me conclude. So we've talked about the origins of the universe. I've reminded you we still know lots about the physical creation, and that exoplanets are being discovered every day, and that we need to integrate those into our understanding of God as creator. We've talked about quantum technology. I've told you this new quantum technology is coming very, very quickly, and it's going to revolutionize the way we think about computing, the way we simulate nature, everything. We are entering a new place. It's still a place where God is sovereign, but we need to work that out in fresh expressions. We've talked a bit about randomness and certainty. I've alerted you to how solid, apparently well-designed things have got randomness at their very heart, and this gets us to think again about design, emergence, perfection. We've talked about the mind-body problem. I've told you about this exciting discovery of the membrista, and how electronic brains are just around the corner, and how that's going to allow us to think a lot more about consciousness and the theological questions associated with it. We've talked about the philosophy of science. Why is it that physics and maths work so well? No surprise to the person of faith. And we've talked about fine-tuning. Why is it that life is possible? The fundamental constants of physics have to be fine-tuned for that to be so. To somebody who believes in a creator God, again, there is no surprise. With that, I'm going to thank you very much for putting up with some physics, for listening so attentively, and wish you a very successful rest of the conference. Thank you.
Thank you, Dr. Russell Coburn, for this excellent talk. As a physicist and as a strong believer in Jesus Christ, he could communicate to us 6 areas where we have a lot of questions and a lot of answers too. So the fine-tuning which helps the sustenance of life in this universe, that is the truth in which we all believe. So thank you very much. Now I invite questions, suggestions, comments.
Hi, professors. It's nice hearing you. I'm Akson Kulin, presently pursuing my in philosophy of science from IIT Mumbai. I have some questions to ask regarding that origin question of the universe. Firstly, how can we say that something come out of nothing? And if the current understanding of physics is taken into consideration, and if quantum vacuums is supposed to be the origins of the universe, then how are we supposed to relate with that the questions of God? Always been thinking, might be God might have some kind of matter which is somewhat temporarily dependent on him, or ontologically dependent on him, from which he created the universe.
Okay, so there's an old school of thought which intervenes at a critical moment to set things going, and then science takes over. I think we need to avoid that, especially very tempting to the beginning of the Big Bang. I think I want to leave God in the picture everywhere. You are right, though, that certainly modern physics has very little to say about the ex nihilo nature of the creation of the universe. The Big Bang theory starts with assume there is a hot dense state that is expanding, and doesn't really deal with that question of how come at minus delta t there was no matter, and then suddenly there is lots of... People do talk about where you can have a particle and an antiparticle suddenly come into coexistence very temporarily. I mean, that is good physics. That is sort of the Feynman view of the quantum background. And then somehow they get separated and so originally you had nothing and now you've got something, and they stay as something. But I wouldn't say it's worked through into anything like a developed theory. It's more just a general indication. So I would say that modern physics doesn't really have anything to say about the ex nihilo creation, whereas obviously people of faith do.
And then, in relation to that, I just want to point in the questions that could it be plausible that God gets something from which the universe is created, could be an entity which is ontologically dependent on God. Not in the sense of being ontologically independent, but dependent on God.
There's a word on this there. Is it ontologically, are you saying?
Yeah, ontologically dependent on God, from which God might have created the universes.
Okay. I think I need to think about that for a little bit longer. Maybe we can talk over lunch or something like that. I don't think I've got an on-the-spot answer for that.
Thank you.
Thank you.
So I see two hands, one at the back. Father, please.
Yeah.
Let me introduce myself. I am Father Gregory Matthew from Dharmara Vidya Kshetram, teaching philosophy of science. Professor, I have a question. According to Big Bang theory, the universe is expanding, and due to this expansion, only space is created. So, could you please give some insight to which realm or into which what this universe is expanding? I hope you got the question. Into which realm or into which that entity to which this universe is expanding? According to Big Bang, universe is expanding, and to which this universe is expanding?
Sorry, I haven't quite got the question. The universe is expanding, but into what?
As it is expanding,
To what realm? What do you mean by realm? What type of realms might it be?
yeah, that's my question.
Can you define how you're using the word realm?
Yeah, there should be something now when it is expanding.
To what extent?
Oh, I see. Okay, I think I understand. So the idea is if I had like a vacuum chamber and I suddenly released a puff of gas into that vacuum chamber, but there has to be something for it to expand into. Is that the essence of the question?
I think the question deals with time, distance, and space.
Yeah, thank you. Yeah, absolutely. Yeah, understood. Thank you. Okay, so the physics understanding of this is that itself, which is both created and expanding. So there isn't anything on the other side of the expansion. It is the very nature of existence that is increasing. It's very hard for us to get this intuitively, but when people say, what was before the Big Bang? The physicist says, well, you can't ask a question, what was before the Big Bang, because before is a temporal word. Time is one of the things that was created in the Big Bang. So, likewise, there is no space, there is no time beyond the universe, and so we can't really ask, what is it expanding into, because there is nothing it can expand into. It's its own being which is expanding. And this was why, when Hubble and Lemaitre first made these observations that the universe was expanding, it was so difficult to believe, because it raises questions exactly. Two possibilities that faced Hubble and Lemaitre was either it's expanding away from us and that we are the center point of the universe, which is possible but unlikely, or that the entire fabric of space-time itself was stretching. That we have today in physics.
Reverend Moses. So we have time only for 2 questions more after this.
So thank you for a wonderful presentation. So, you talked about the faith and the physics. So Stephen Hawking always tried to prove the another world. Fortunately, unfortunately, couldn't conclude during his lifespan. So, as a scientist, what is your opinion about the possibilities of another planet or another world from the line of Stephen Hawking?
You're talking about life on another planet? Yes. So, my personal view, and this is purely speculation, I have no proper scientific evidence to draw on, but in terms of looking at the data and what do I think is the most likely trajectory, I think we may well find life on other planets. In its earliest form, it's most likely to be a very, very simple biological life, some little microbe that can convert one gas into another gas, something that we would hardly even recognize as alive. So I'm not talking about little green men or anything like that, but just some little bit of slime mold. I mean, it is possible that there aren't any. It is possible that this planet is the only place where there is life. My best guess is that we may well find other places. So whether we find intelligent life elsewhere, that's a different question. I mean, one of the big arguments against that is the so-called Fermi paradox, which says that, you know, if there is intelligent life on other planets, why haven't they contacted us? Now, it is possible that we are the most advanced form and that they don't have the telecommunication means to do that. But that would seem odd because human life actually was quite slow in starting. If there is life on other planets, there is a fair chance that it started several billion years before human life did. And therefore, you might expect that their technology would be more advanced and that they are capable of communicating with us. And yet they don't seem to have done, which might say there isn't any. Don't know, but these are the sorts of arguments that people make. I think the interesting theological question that we can ask now is, what would our theological position be? You know, we can prepare our answer in advance. And I think actually we have the theological tools to do that. We know that if there is other life on other planets, that God is still the creator of it because he made everything. Nothing was made without him that was made. I take that to include. There's then the question of to what degree does Jesus' death and resurrection redeem that life? But I think we have the theological tools to prepare an answer.
Yeah, here, only two hands are here. Yeah, madam. Yours, madam.
I'm Cynthia Stephen. I'm a journalist. I'd like to ask whether, there has been some change in the way technology has interacted with humans. Like from analog, we moved to digital in a generation, and now we are going to nano technologies. And I understand that the past 20 years since the internet, the digital natives, one generation of digital natives have been born in this country, in this world. So the way the younger generation interacts with technology, it's almost natural, like fish in water, swimming in water. Whereas it's so much of a struggle for older people. Is there an impact of exposure to technology on our brain? So it's not about constructing a trans brain like to imitate the human brain, but is human brain going to have morphological changes as a result of access to technology? And will that be a good thing or not a good thing?
I mean, I'm not an expert in that. I think you need an evolutionary biologist, maybe Dennis can talk about that at some point. But I guess there are two ways in which it could interact. There's the short-term interaction. So people worry, for example, about whether children are more likely to be short-sighted because they spend time looking at a screen close up during developmental years rather than running around outside looking at things in the distance. The expectation being that those wouldn't be passed on to the next generation. That would just be a single generation event. And then you've got the more evolutionary questions about will humans, over many generations, evolve in a way which is better adapted to the technologies that we have. I mean, I think there is evidence from the animal world that other animals have evolved in that way. I think there are examples of moths who've evolved in the colour to blend in with smoke from factories after the Industrial Revolution and things like that. So there's no reason why we shouldn't do the same. That evolution is driven by the environmental niche we find ourselves in, and if that environmental niche is one dominated by technology, then we should expect to find that the course of evolution adapts to that technology. As to what that really looks like, I've got no idea. I certainly wouldn't rule it out. I mean, there's also the other side of that question. In a way, the technology stops us from changing. So, I mean, the example I often give is my terrible eyesight, which is of genetic origin. And before the technology of optics, of glasses, these bad genes should have been removed from the gene pool by grandfather's grandfather being eaten by a bear, which he didn't see coming. Put glasses on, it means that genetic defect can propagate forevermore. And there are many other examples of where medical interventions stop the natural selection that would normally be refining the gene pool. So that's another way in which we might find technology modifies the humans by allowing defects to become livable with.
Yeah, so you.
Thank you very much, sir. In describing quantum technology 1.0, you made a statement, randomness leads to completeness or perfection. And in mind-body problem, you talked about neuro. My question is this principle of randomness leads to perfection can be seen in neuromorphic architecture of mind? And does this structure anything about the intelligent design as per your understanding?
Really interesting question, thank you. So, yes, certainly to the first half of that, let me give you an example. If I take a simple my mobile phone and I calculate the square root of a big number, it will be precise. I will get 10 decimal places on the screen and they will be absolutely precise. If you ask me as a human to take the square root of that number, I might be able to estimate it. You know, I know the square root of 1,000 is roughly 30, but I know it's only roughly 30. So at first sight, you'd say, well, the human brain is not as accurate. It's got more errors than a digital computer. And that really gets to the heart of the difference between a von Neumann architecture, which is what my calculator is using, versus a neuromorphic. But on the other hand, there are so many things the human brain can do far better, much more precision than the digital computer could be. So for example, even though we've just met, tomorrow I will still recognize your face in a way that my mobile phone will not. We have to redefine what we mean by accuracy, a good computation. And it's no longer about getting the decimal places right, it's about whether it can suitably complete a complex task. And I think that's one of the things we definitely will see change. We will redefine what we consider to be. As to where that points to intelligent design, no, I wouldn't say that at all. Yeah, I think that's what I can say. No.
Okay, the last question of the session.
One small question. Sir, do you want to be an atheist to believe in multi-universes?
Do I want to?
You want to be an atheist to believe in multi-universes?
No, I don't want to believe in multiverses, and I don't want to be an atheist. Because I don't think there is any empirical evidence for them. I think it's purely a mathematical construct, and I don't think there is much possibility there ever could be empirical evidence for them, because by definition they lie on the horizon, and so we could never have any data about them. So to my mind, this is the difference between being a physicist and a mathematician. As a mathematician, I'm free to postulate whatever manifolds I like. As a physicist, I'm only free to postulate those things which, at least in principle, I stand a chance of being able to falsify. And since I can't falsify the multiverse, I don't want to think about it.
Thank you, Professor, for your talk and giving answers to the questions. I know many people have got many questions, but we have one more session.